So to start off chapter 9, we look at simplifying radicals and different ways we do that. So today we're looking at simplifying and multiplying radicals. A radical is using this symbol. All right, it can also do like cube. This is a square root, which most of you are probably familiar with. You can also do it with cubed roots or fourth roots or anything like that. All of those are radicals. And there's slight differences, but basically all the rules we would be going over apply to all of them. But we're basically just going to be looking at square roots. So when we simplify a radical, it says a radical is fully simplified when no perfect square is a factor of the radicand. Okay, we'll expand on that a little bit tomorrow. But for what we're doing here, that's a good definition. Perfect square is a number where there's a certain number that multiplied by itself equals that number. So like the square root of 25, most of you know, is equal to 5. So root 25 is a perfect square. Root 8, which we have here, is not a perfect square. Okay, because there's no whole number that I can multiply by itself to get 8. Okay, and actually it'd be like a repeating decimal if I tried to come up with it. But, all right, actually I'm going to use a different number here. Let's use 24. All right, if I look at 24 is, and there's different ways you could do this, is 4 times 6. 4 is a perfect square. So 24 has a perfect square in it. So the simplified version of this is 2 root 6. Okay. I'm going to go over how we did that with the examples. So there's a couple ways you can do this. A lot of the Algebra 2 classes have you memorize your perfect squares, like 4, 4, 9, 16, 25, and then look for those as factors. That is the fastest way to do it if you see them, right? If I can see that 24 is 4 times 6. But some people will look at 24 and see 3 times 8. That's now harder to see. So a tool you can use is a factor tree. So we look at 8, right? 8 is 2 times 4. 4 is 2 times 2. If I have a pair of numbers, since I'm doing square root, I can take that pair of numbers out. So these 2's come outside of my radical. 2 squared is 4. That's why I can take that out. Anything that's not paired up stays inside. So we look at 12. If I'm looking for the perfect square, it would be 4. Okay, but a lot of people, when they see 12, will do 2 and 6. 6 is 3 and 2. Right? So I have a pair of 2's. That pair comes out as 1, 2. The 6 doesn't count because I factored that. The 3 is still there. That goes inside my radical. So 2 root 3 is my simplified version. Okay. This is a tool. So 27 is 3 and 9. If you look at 9 and you go, oh, 9's a perfect square. I know the square root of that is 3. Then you can just put 3 root 3. Okay. If you need to factor it to the 2 3's to get your pair, that's fine. Okay. Also, the advantage of this is if you're stuck on what goes into it, it makes it easier. So 48, there's a whole bunch of numbers that go into 48. But I'm looking at 48 and I don't know what goes into it. So I'm going to start with 2. Right? So 2 goes in 24 times. And we'll just keep doing that. We have 2 and 12. 12 we actually already did, so I could use that if I wanted to. Here we have 4 and 3 and 2 and 2. Right? So I have a pair of 2's here and I have a pair of 2's here. One of each of those pairs get pulled out. So I have 2 times 2, that's 4. The 4, the 12, the 24, none of those matter because I factored them. But the 3 is by itself. So the 3 stays in. And my simplest radical form of 48, square root of 48, is 4 root 3. Okay? If you're looking at perfect squares, the perfect square here would be 16. 16 times 3 is 48. Okay, so one of the advantages of the tree is you don't need to see them. We also use that when we look at the next thing, which is the multiplication. All right? So I can look at it as either a times b or the square root of a times the square root of b. So 500. Okay? Now you would just do the factor tree on this, but this is 5 times 100. 100, okay, is a perfect square. Most of you probably know that the square root of 100 is 10. So the square root of 5, or 500, oops, I did that backwards, is 10 root 5. All right. 8 times 2, I can factor it from that if I want to. But 8 times 2 is the square root of 16. Again, if you don't see it, do the factor tree. But if you think about it, you all actually know that the square root of 16 is 4. Right? You might need to refresh your mind on that, but that's something you're familiar with. Okay? If I have something like this, the numbers outside deal with the numbers outside. The numbers inside deal with the numbers inside. So 2 times 3 that are on the outside gives me a 6 on the outside. The 3 times 2 that's on the inside gives me a square root of 6 on the inside. Okay? And now the square root of 6 does not factor. Right? 3 and 2, there's no pair, so this is my final answer. The square, when we're squaring it, okay, root 5 squared. There's 2 ways you can look at this. Okay? Now you need to be careful because of what we'll talk about on E. But if I just have the square root, I can basically look at the square and the square root as canceling. Right? So the square root and the square cancel, then I get 5. If you struggle with that, square the number inside. You get the square root of 25. Square root of 25 is 5. The thing to watch is on E. Couple things to watch here. One, where are the parentheses? This is different than this. This problem here, root 7 is being squared. Root 7 squared is 7. So 2 times 7, that's 14. That is wrong for this problem. The whole thing is being squared. So 2 squared is 4. Root 7 squared, actually I'm going to put this down here. Root 7 squared is 7. Again, if you have trouble seeing that, 2 squared is 4, 7 squared is 49, but it stays under the square root. Take the square root of 49, and I get 7. 4 times 7 then is 28. Ooh, which I can't see. It's 28. We can also look at this with problems. Right? So we have x squared plus 7 equals 6. Basically, I just solve that like I'm doing a normal problem until I have x squared by itself. So I subtract the 7 from both sides. Right? I get 8x squared equals 9. So I take the square root of both sides. I get x equals 3. Okay? And in this case, it works out to be a perfect square. That won't always happen. So you may have things where you have like 3 root 2 or something like that there. On something like B, we're cross multiplying. So 2 times 18 is 36. X times x is x squared. And then I take the square root. So x is 6. But if we come over to C, again, x squared, 8 times 5 is 40. Right? When we take the square root of 40, we get 2 root 10. All right? And I'm fine if you know what the square root of 40 is and get 2 root 10, I'm fine with that. right? Most of you probably will have to do some sort of factor tree there. What I did is the reason I knew it is it's 4 and 10, right? I have a pair of 2s that come out as my 2. I have a 2 and 5 that stay in. They get multiplied together, and that's where my 10 is. Okay. All right. Then we have the things down in the bottom that are simplifying. Basically, I want to put the answers here. If you have questions on these, let me know. But this should be 12. What's that? Right here, I have 20 times 5, or 20 times 1/5, which is 4. All right, I have 50, which is 5 root 2. Root 3 times root 8. This is root 24, which I think we looked at the front. Oh yeah, that's this one. Right, so we already said that was 2 root 6. All right, root 16 times root 4, which is 8. 3 root 5 times root 2. Remember, the roots deal with the roots. The whole deal with the whole, so the 3 stays by itself. And I have 3 root 10. 7 is 2. 8, 16 times 3, which is 48. Right? And then x squared will equal 36. So x equals 6. And that is our introduction to radicals. Tomorrow we're going to look at fractions, which is a little bit harder, but we'll go over that tomorrow.